Welcome all to the third live session. Today we will again discuss certain problems based on the results that has been discussed in the previous class. Share my screen now. Okay, so I think the screen should be visible now. So here is the first question for this tutorial. We are just going to repeat certain questions about separability because we could not discuss a lot about separability in the last tutorial. So first question is, when do we say a finite extension is a separable extension? We'll think for a minute and then we will discuss the solution. Alright, so here is the solution. So we say a finite extension K over F is separable if and only if for every alpha in K, the irreducible polynomial of alpha over K is separable. That means all its roots are distinct. Right. So all its roots are distinct and then we say that the extension is separable. Right. So I guess definition is a repetition. So this all of you must know. Now, what are the few examples of separable extensions? Can you recall? So maybe you can think and write in your notebook and then we will discuss the solution. Yeah, so if you can see that Q root 3 Q, or let's say Q 2 power 1 by 3 omega Q, or in fact any finite extension or characteristic zero field is always separable, or maybe any finite extension of finite field. P is also a separable extension. So all these are repetition of what we discussed a little bit in the last tutorial. So I think this question is more or less clear. Okay, let's go to the second question. So second question is, we have to give example of degree 2 extension which is not separable. Which is not separable degree 2 extension. Can you recall of some extension which is degree 2 and not separable? At the same moment, you have to give example of degree 2 extension which is separable. And third is, what are perfect fields, and give some examples of perfect fields. So hint is this has appeared in lecture notes also, and the example was also a degree to extension only, not a higher degree, but degree to only. Okay, so let me recall. You take F2T. Recall, maybe before this, let me recall what is F2T. F2T is the quotient field of the ring of polynomial in one variable over F2. That means it has all those elements like Ft by Gt, where Ft and Gt's are polynomial in one variable, let's say t over F2. Coefficients are from F2. Right. So of course Gt is non-zero. So we will use this field. This note that the characteristic of this field F2T is 2. So we will use this extension. Now, first of all, how it is an extension, because we need to say that the lower field has to be contained inside the upper field, right? So note that root t belongs to in our top field, right? This top field contains root t, and any power of root t is also contained in the, because it is a field. Therefore, 2 belongs to F2T. But F2 also contained in F2 root T, right? How? All constants, right? Because this is the ring of a field of, in fact, polynomials, quotient of polynomials. You take GT to be 1 and take F2 to be all constants where C belongs to F2. So this will tell that even F2 is there. And you know that F2T is the smallest field containing F2 and T. Therefore, if both are there in this, therefore the field generated by that is also contained in this. Therefore, we can consider this tower field. So the tower is good enough. Now, why is not separable? This is the crucial fact that why it's not separable. Why? Because root t satisfies x square minus t irreducible. This is an irreducible polynomial over the base field. Yeah, this coefficient is from there, and in fact minus of that also. Right. So this is a degree 2 polynomial, therefore the extension is 2, because the irreducible polynomial has degree 2. Now, uh, moreover, if you see the possible roots, so possible roots of x square minus t equal to 0 is x is plus minus root t. But notice that characteristic of our field is 2. This is important. This is an important fact. And using that, root t plus root t is 0. Because this is twice of root t and 2 times anything is 0. Therefore, root t is same as minus root t and both roots are same. So look at the definition once. Definition was that all its roots are distinct. Irreducible polynomial should have roots distinct. However, our roots are same. So the extension is not separate. I think this is clear. Now one has to write an example of degree 2 extension which is separable. I think this is easy. Think for a minute, write your own examples, and then we will discuss the solutions. Yeah, if you see, as we know that all this is a example of finite field. It's a degree two of sorry. Yeah, so this is degree two extension field of FP. And any degree two extension field of FP has to isomorphic to FP square. This is what structure theorem says. And therefore, we can say, moreover, one can also say that this is always separable, or any degree two extension of characteristic 0 is all our degree two extensions which are separable. So, right, I think this is pretty clear. Now you can think for a minute that example of perfect field and what are perfect field first of all. It's not difficult, I guess. This has been done in the lecture classes also, that the definition perfect fields somebody who's waiting for this. Yes, no one is there. Yeah, so definition of perfect field is, so either so characteristics 0. Well, definition is not like that, so maybe I'll write the precise definition. So a field K is said to be perfect if the Frobenius map, if the Frobenius map is subjective, is phi from K to K, Frobenius surjective. That is, for given any x in K, there exists a y in K such that x is y bar p. If that is the case, we say the field is perfect field. And I guess you must know the examples are all characteristic 0 fields, finite fields, and there are more, but let's say for time being, we have these many examples. Yeah. All characteristic 0, finite fields, all are perfect fields. Right. So I think this was all about question 2. Now let's go to question 3. Question 3 says, suppose the polynomial is xp power p minus t power 10. This belongs to fpt x. So this is my field. Let's say k, just like we have kx. It's like that. So your coefficients are from this. Coefficient is like this, and discriminant is, sorry, indeterminate is the x. Right. So is fx separable over fpt? So we want whether our function, I mean the polynomial, whether it is a separable over fpt. Recall, separability means all its roots are distinct. Can we say that? Yeah. Well, I think you can try that this is not separable. I take, let's say, p to be 3, let's say. Let's take, okay, then your fx is x3 minus t power 10. Right, this belongs to f3t of x. Right, it's a polynomial in x from this field. Coefficients are from this field. Coefficient is this is from the field. Right, so if you look at f clearly, then I mean very carefully, then you will realize that this is same as this. And this is why, think for a minute. Yeah, so if you realize, then this is because this is minus 3x squared t10 by 3 plus 3x10 t10 by 3 square minus t power 10. If you expand this cube, then you will get this, but you know that the characteristic of f3t is 3. This implies your fx is just x cube minus theta. So indeed your function polynomial is 10 by 3 cube. The polynomial is like that. So if you can see carefully, then all its hello.
Hello.
Yeah, so I guess you are late today, but
No, I
I
have
have.
experienced a difficulty in entering.
Okay. So okay, I'll try to repeat what I did. So let me share my screen. I think you can see it now, right?
Yes, see, I
Okay,
can
so I'll
see
go
now.
back. Okay, I'll just quickly go back what I did. So question one is about separability. I just recalled this all these facts because I we could not discuss nicely about separability. So first was
Are,
about yeah,
are you recording? Are you recording?
yeah, this time I am recording. Yes.
Okay, just a reminder.
Yeah, thank you. So first is when do we say a finite extension is separable? That we have seen that for every element inside your bigger extension, let's say k, the irreducible polynomial should be separable. That means all its roots should be distinct. So then we say what are the examples? Examples are we know that all finite extensions of characteristic zero field are separable, and at the same moment, all finite extension of finite field is also separable extension. So all these examples are separable. Right. So then we saw that what are the examples of degree two extension which is not separable. Uh, so I think this is also roughly we discussed. So I'm just repeating it again that in this case also we can see that this is the extension which is degree 2 and this is not separable because of root t has this polynomial which is irreducible. However, its roots are not distinct because of characteristic is 2. So then roots will be same and therefore repeated roots are not there for a separable polynomial. Therefore, this should not be a separable extension. I think this is clear, right?
Yes.
And anyway, we saw examples of degree 2, and anyway, one can construct degree 2 extensions also, which are separable. So all such are characteristic 0 extensions, which are degree 2. Therefore, all are separable. And this is one example of finite field, which is also always separable. We know that. And then we saw what is the definition of perfect field. So a field is perfect if this map is it's a surjective map. So given any x, if I can find a y such that every element is a p power of some element, then we say that is a perfect field. And examples again are characteristic 0 and finite fields are indeed perfect fields. So this is all kind of repetition. So I think it's more or less clear. Yeah, now this is also discussed, but then this could not be recorded in the session. So I re-recorded the second session, which I forgot to record. In that, this question was not there. So I thought that I better take this in the next tutorial. Yeah, so I was discussing this. So is this polynomial separable? This is what we want to know. So important fact, whenever we take a polynomial like this, x, let's say xp minus t power something inside fpt, then note that we usually take the same p which we are raising the power because we want to use the characteristic of this field to be p. So we want to use this fact and we want to make sure that this being like this can be realized. And in that we will use that characteristic is p. Therefore, this power and this characteristic, whenever you see that to be same, so your first guess should be that this is not separable. Yeah, so this is how we construct non-separable extensions. So, right. Yeah, so we can see here also our polynomial is has repeated roots. So f has 3 repeated roots. So therefore, f is not separable for f2t.
So 3 repeated roots where?
Yeah, so all repeated roots are t10 power 1 by 3. Right? This is the
These are
polynomial.
the roots where they are.
Yeah, so we want to say separability means wherever it gets split, there it should have all its roots should be distinct. So just like where should I saw where did I see? Okay, so maybe I think in the extension field I should write in FP T10 by 3. This is clear, right? Now is it separable over this extension FPT 10 by 3? So of course it has one root, but all its roots are same, right? So therefore it cannot be separable. Does it make sense now?
Okay. Now I have a doubt.
Yeah. So can you please repeat
Can you
what I?
say GCD of a polynomial, comma, 0 polynomial is that
Polynomial.
polynomial? Can we say so?
Sorry, I don't get you. Your point. GCD of given
GCD
polynomial.
of one polynomial f of x, comma, 0,
Uh-huh.
0 polynomial.
Yeah.
This I say f of x.
Can you say this? This is question.
Can we say so?
No, right? Because
Hmm.
how? Okay, how do you say that the greatest common divisor inside your 0 is fx? Because are you trying to say this 0 equal to 0 time fx and therefore it is?
Yes, because any polynomial divides 0.
Right, because you can write anyway your 0 times fx, any fx,
Yes.
yes, right.
So f of x divides f of x.
Okay.
And
So,
this,
okay. Okay. If this is true, then what do you want to say more?
that is GCD is this is not equal to 1. Suppose if
Well,
f
well,
of x is not equal to 1,
but you want to say about f and f prime, right? In order to say,
yes,
right?
then when the GCD of f of x, suppose if the derivative is say 0,
Okay, okay.
f of x derivative is 0,
Mm-hmm, mm-hmm.
then GCD of f of x and its derivative is not equal to 1,
Right, right. And therefore, you can say that it's not separable.
not
Correct.
separate.
Right, right.
Okay.
Yes.
So my problem is whether we have to talk GCD only for two non-zero polynomials or zero
Uh,
polynomial is allowed.
okay. Maybe I will check this fact. Even I'm not sure. So
Oh,
maybe I will check. Yeah,
okay, madam.
yeah. So next time, I think I will clear this fact. Yeah.
Okay. And now the conclusion is for this problem, x cubed minus t power 10
Mm-hmm.
is not separable because of that characteristic 3, right?
Right, right. You're right. Yes. Okay. I will see whether this kind of argument is allowed to give or not. So I think
Hmm.
I'll clarify this in next class. Yeah.
Okay.
All right. So now next question is about stating fundamental theorem of Galois theory. I think this is recently discussed in the class. So this is one of the important results that we have in the Galois theory.
Yes.
So if you can recall, so then we can discuss here what is that. Yeah, so let me just recall quickly. So this is about, okay, I'll just give you a rough sketch and then we will write it precisely. Anyway, I've written, I'll show you that. So there is a bijection that we want to define between,
Screen is not visible.
sorry, screen is not visible. Okay, I will see. Is it visible now?
No,
What about now? Is it visible?
no.
I think there, I also have certain issues regarding this network here also is not that good today. What about now?
Yes, it is visible
Okay,
now.
okay. Yeah, so, right, I think this part is not true. What I can recall and see some notes that 0 is not allowed. So f and g, if they are non-zero polynomials, then
Hmm.
only you talk about f and g. So we talk about, okay, let me just write here. So this is not a correct way as we talk about GCD of two non-zero polynomials only. Yes. So your doubt was correct. So we don't talk about zero polynomial. So then one has to go through this way only. All right. So let's go to this fundamental theorem of Galois theory. As we said, it's a result which gives a bijection between subgroups of G. I will tell what is G and intermediate fields. And how this is, suppose we have K over F is a Galois extension, and then we have this tower of field. We want to know what are the possible subfields here. So on, we want to know what kind of fields are these in between K and F, knowing that K over F is a Galois extension. So sometimes looking at the fields is not easy to see what are the all possible subfields, but we can use a result that let's say
That
G is the Galois.
intermediate fields including K and F.
Yes, intermediate fields of K of F. Let's say I should write precisely intermediate fields between F and K. That means that should contain F and that should be contained inside K. Right. So thus, if we know this, we know that the Galois group of K over F is G. If K is written at the top, we will write G at the bottom. This is how we try to write. So then we know that this is the group whose fixed field, if I take K, then this is always K, right? If you see. So if we just take the trivial automorphism of K, it will fix K, right? So therefore, K fixed field with a trivial group is always K. This is okay, right? So in between, we want to know the subgroups. This is which we want to know. So once we have subgroup, the theorem says we have a field also. So whenever we have a group, possibly there are many subgroups. There are many subgroups. And the result says each subgroup should give me a field. Each subgroup should give me a field, let's say L1, L2, L3, such that F is contained in L1 and contained inside K. Same thing for all. F is contained in L2 and so on. So this result is quite nice in the sense, suppose we don't know all possible subfields, we cannot see directly suppose, but we know the group structure, and suppose we also know all possible subgroups there, then we can also construct their possibly fields. And how to construct the field, that is also given in this theorem. So how to construct that? Let me just precisely write it now. Yeah. So suppose we have this Galois extension and G is the Galois group. Then there is a inclusion reversing because you have, suppose you have K over, sorry, I think this should be F. Yeah. So if we have K over F, then that group is nothing but G. However, if I take a smaller field, let's say K over KH, the group is H. So the field is bigger, but the subfields over which we are considering.
Excuse me.
Yeah.
Moreover.
Yeah. Moreover, so before that, there
H
is
or
how to.
K. H or K.
No, that is correct. K is to KH is H. That's correct.
K over K, which is equal to number of elements in K or number of elements in H.
Yeah. So this is K over KH is same as order of H. Yes, this is true.
Order of?
Sorry. Hello.
Order of H or order of K?
No, order of H only. K, what is K? K is a field, right?
No,
We
we
don't.
have written K there. That is what I am telling.
No,
In
this
the
is H.
box.
Sorry, this is my H. Sorry, this is my
Okay.
H. Yeah,
Hmm.
sorry. That is H. That is H.
Yes.
This is how I have written. This extension is same as order of H. Yeah. Right. So that is H. I think that is also a mistake. Not mistake, but notation wise not clear. Okay. So suppose we know group, then how to construct that intermediate field? You take the fixed field by that group. That will give you a subfield of K containing F. And if I have a field, let's say, suppose we go this way. Suppose we know field. How to get the group? We take the Galois group of K over L, not K over F. Because, why? Because we know that K over L over F, we know this is Galois, then this may not be Galois. This we know. But this is always Galois. This is right, right?
Yes.
The above one is always normal as well as separable and therefore Galois. So that's why we can talk about that group, K over L. So this is how the bijection work. And moreover, we can also get the degree of extension through the index of the subgroups. So the above one which we got, I think I'll highlight. This one is having order h. And the later one we know that because of the fact that k over f is same as k over kh times kh over f. However, this is mod g. This we know mod h. This has the possibility it has to be mod g by h, right? So this is how we get the lower one has to have this index, right? So this is the first part of the theorem. Other part says that we know that in general the this lower extension need not be normal. In general, that means it need not be Galois. So the result says that it can be Galois provided we have some assumption on the group that we have. So we know that if we have this intermediate field, then we have an intermediate subgroup also. That subgroup we are calling that to be H. So we want to say whenever this subgroup has certain property, the lower one will be become a Galois group, Galois extension. So the lower will be a Galois extension provided this subgroup is a normal subgroup. So therefore, um, this is Galois. This if this group Galois K over L, that means the group H. This is same as the group H, right? Because L gives me a group here, and that group is nothing but H, right? That group is normal subgroup. If in G, then we say the lower one is also a Galois extension. And what is the Galois group? Now, next question is what is its Galois group? Galois group is nothing but G mod H. Note that H is nothing but Galois of above extension, K over L. So either you write G mod H or you write the Galois K over L. They're the same thing. So notation wise, there are many things to consider. Like one has to give some time in order to digest this theorem. There are several things. Hopefully this is clear, right?
Okay.
All right. So knowing this result now, roughly, we will use such results somewhere in order to know the subfields or subgroups, something like that. Okay, so if we recall one result that K over F is a finite extension, and then K over F is a Galois extension if and only if K is the splitting field of a separable polynomial over F. This is one statement that has been proved. So there is one more equivalent relation saying that K over F is a Galois extension. So if we can realize K to be a splitting field of certain separable polynomial, then it is always Galois. So can we use this equivalence to check that whether the given three extensions are Galois or not? So this is first extension Q2 per 1 by 3 omega over Q, where omega is primitive, third root of primitive. So what can we say about this? Is this Galois?
So you want to apply that result to this is
Yes,
called if and
yes,
only if it is a
yes,
splitting field of separable polynomial, right?
yeah, right.
So this is of degree 6, right?
This is degree 6, exactly right.
Degree 6. So we can look for a separable polynomial.
Yeah. So can you find a polynomial whose splitting field is this and polynomial should be separable polynomial? So remember that I'm just recalling that if you have certain extension, that extension is always the way we construct is always including roots of a polynomial, right? We add roots of certain irreducible polynomial over Q to it, and this is way we get the extension. So look at the roots and look at what are their irreducible polynomials and try to construct a polynomial from that such that its roots are these only and that has to have all distinct roots and this extension should contain all its roots. This is what roughly we need. So if I ask you, what is the irreducible polynomial for this extension?
X cubed minus 2.
X cube minus 2. What is the irreducible polynomial at this level?
That level, say 1 plus x squared.
Exactly, 1 plus x square. And what are its roots? All roots,
Omega no, roots 2 power 1 by 3.
right?
2 power
And
1 by
what,
3 omega.
yeah,
2 power 1 by 3 omega squared. These are the three
yeah,
distinct
these are
roots.
right. These are all three distinct roots. What about other polynomial? What are its roots?
Omega and omega squared.
Omega square. Can you see one thing first of all? The polynomial that you have taken, all does it all roots lies in your splitting field? I mean, in your extension. Let's say this extension. Does it contain
Yes,
all your roots?
yes,
Why? Because it's a field. So if we know that it is a smallest field containing 2 power 1 by 3 omega,
and omega.
this, yeah, so this at least we know that belongs to. Then the product is also there because it's a field. So this element is also there. Same
Mm.
thing, this element is also there.
So
And therefore
all
omega.
five roots are there.
Right. So therefore we can say this is at least we can say this is a splitting field, right? Of what polynomial? Can we write what that is the polynomial?
Product of these two.
Exactly right. So we will just write x cube minus 2 times 1 plus x square. Right. So this is a splitting field of this. Or moreover, you can say that this is also a separable polynomial. Why? So polynomial is separable. Recall. So f is separable over k over, let's say here it is f, if
Each
let's
of
say
its irreducible factor.
exactly. So if you have fi's are and all are irreducibles and all irreducible factors have distinct roots in the extended field, then we say f is separable. Let's say separable where fx is in fx separable over k, I guess, right? Uh, am I not making mistake, right? If I am making mistake about this field, that you can clarify. But
Separable over Q.
okay, f then should be f. Right? Yeah. So that means your all irreducible factors should have distinct roots. Should have distinct roots. So if you can see, I mean, for separability, we don't need that which extension should have. We just need that roots should be distinct. However, for splitting field, we need that all its roots must lie in our extended field. So from both the results, our all roots are there in the field. Moreover, it is a separable polynomial because of all its irreducible factors have distinct roots. This is F1, this is F2. Therefore, we can say it is a Galois extension. What about the B part? So B part, let me write. B part is Q 2 power 1 by 4 over Q. Can we construct a polynomial which has root this 2 power 1 by 4?
So in the first part, what is our conclusion? Q of 2 power 1 by 3 omega is
Is a Galois because of this result, because it is a
yes.
splitting field of a separable polynomial. Therefore, it is a Galois extension, right?
Over Q.
Over Q, yes, over Q.
So the corresponding polynomial x power 4 minus 2.
Yeah, exactly. So 2 power 1 by 4 is a root of an irreducible polynomial x power 4 minus 2. So if theorem says that it should be a splitting field of a separable polynomial over f, but if you want to split your polynomial, then it should have one root at least, right?
Yes.
So we say a splitting field, that means if it has a root, then it should must be there. And we have one polynomial which has one root there. So by result, if at all it is Galois, then all its roots must lie in our extension field, right? So if Q 2 power 1 by 4 over Q is Galois, then by result, then Q 2 power 1 by 4 should be a splitting field. We want it to be some separable polynomial, but let's look at splitting field of at least some polynomial. However, we need separable. At least this should be there. We need more also, we need separable also, but at least split. But this is one polynomial, and any other polynomial, if it, let's say there is one more polynomial which has 2 power 1 by 4 as a root, then you can check that that should over Q, and you also notice any polynomial over Q which has 2 power 1 by 4 as a root, coefficient should be from Q, that should be multiple of this polynomial. This is the least degree polynomial which has root over Q. No less than this degree can be a polynomial which has this as a root. So, knowing all these facts, we know that the only polynomial choice is this or some multiple. This we know. So, in order to say this is a splitting field, both these polynomials should split. Let's look at the simplest one, that means x power 4 minus 2. This should split, but all its roots are, what are its all roots?
X 2 power 1 by 4
Hmm?
minus 2 power 1 by 4
Hmm?
2 power 1 by 4 times I 2
Yes,
power 1 by 4 times minus I.
exactly. So you can see that these two roots does not lie in our
Yes.
extension. So therefore, what can we say? Is this extension Galois?
Because for every polynomial, The x power 4 minus 2 is an irreducible factor.
Yeah, for any
Yeah.
polynomial which has 2 power 1 by 4 as a root, this should be there. Should be.
So there is an
And
irreducible polynomial factor,
yeah,
irreducible factor, which
mm,
is not containing all q power 2 1 by 4, not containing all its roots.
exactly. So your argument is exactly right because any polynomial which has this root should be of this form. And the simplest example itself does not have all roots. Then we don't need to check the other polynomials. So therefore, it's not a Galois. Not a Galois. We have one more q omega over q, where omega is the primitive third root of NP. Let me write that also. Q omega over q, where primitive root. So can we find a polynomial which has this root over q?
The roots are 1 plus x squared.
Okay, you are writing this one. Suppose I write this one then.
It is okay.
Okay, maybe we will discuss what I want to say by writing this polynomial. Because we need this extension to be Galois by saying that it is a minimal, it's a splitting field, not minimal, splitting field of a separable polynomial. Is it separable over Q? What are its irreducible factors, by the way?
X minus 1, one irreducible factor. 1 plus x squared, another irreducible factor.
Yeah, is it separable?
Yes, because the irreducible factor has only one root.
Yeah, this has only one root. And
So
what about this?
therefore, that has roots omega and omega squared.
Distinct, right? So f has all its irreducible factors have distinct roots. Therefore, f is separable, right?
Yes.
Indeed, your answer is also true. Your polynomial fx is itself is irreducible, and your polynomial has omega and omega squared distinct roots. Moreover, q omega is a splitting field for both the polynomials. Can I say q omega is splitting field of separable polynomial x cube minus 1? Or if I say it's a splitting field of separable polynomial 1 plus x square. Are they both statement okay? Yeah.
So for same polynomial, you cannot have different splitting field, but different polynomials can have same splitting field.
Of course, of course, of course. If I say q root 2 root 3, let's say q root 2, simplest example. If I say x square minus 2 and any polynomial x square minus 1, x square, just x square, x square minus 4, I'll keep writing. So if I say this is my fx, is q root 2 splitting field for fx? Splitting field, by definition of splitting field, can you recall what is definition?
So all its roots are there.
Yeah, roots are there, right? Because
And
roots are
this is the
plus
smallest
maximum.
field containing all roots.
The smallest field containing all roots, exactly. But there are several polynomials which have the same splitting field, but irreducible one. We want irreducible one sometime. Then there is a unique polynomial which will satisfy. Right? This is your irreducible. The only factor different is this is irreducible, mine is reducible. We just need separable. All right. If I add here, suppose if I add here this polynomial, this is not allowed. Why? Because it has a repeated root. X is 1, 1.
One.
So I cannot use this polynomial to say that this is Galois, but I can use this and this both polynomial to say it is Galois. This is okay, right?
Yes.
All right. So there can be several polynomials having same splitting field, but as you said, splitting fields are unique for a polynomial. You cannot have more than two splitting. So
So it is Galois.
yeah, so this, let me just try once again. Hello, not there. Okay. Next question is how to find the irreducible polynomial of an element in a Galois extension. Let me repeat what my question is. Suppose I have K over F Galois. And if I take any alpha in K, then I want to know, I want to know what is the irreducible polynomial over F which has alpha as a root. Is it always simple? I don't think so. This is always simple to construct, but there is a recipe through which you can always construct your irreducible polynomial. Do you understand what I want to ask? Yeah.
Yes. So these are all general fields K, F.
Yes, yes. I'm not giving you what is K, what is F. Later we will discuss, maybe. We will discuss for examples also, just to clarify the thoughts. But for time being, the recipe is for any Galois extension. Note finite Galois. I'm not saying about anything about infinite. The results about infinite are really different than what we think about finite Galois. Yeah, okay. So let me just give some hint. This has come in the lectures. So I pick up
Yes.
this from the lectures. However, I find it very
You have to
nice.
take some sigma 1, sigma 2, sigma n,
What are those sigmas?
the set of all automorphisms on
Yeah,
K,
which are
F automorphisms.
exactly. So if you take the
And then you
Galois group,
take that alpha, sigma 1 of alpha, sigma 2 of alpha, etc.
yeah,
Then you take the distinct elements.
very nice, very nice. So if I restrict my sigma I to F, to that should be identity. This is the meaning of F. Right. So you take all sigma. First of all, you know that this is Galois. This is given. Then only you can consider the Galois group. Then you can consider your sigma i's. Then you write your alpha, whichever alpha you want to find the irreducible polynomial. Look at its image under all automorphism. All automorphism. Take out the distinct one. There can be different, same also. You take out the distinct one and write it is like this. This will be a degree, whatever the polynomial, provided all sigma is. Suppose all sigma is alphas are distinct, then this will be degree n polynomial. And then this is how this is becomes the irreducible polynomial of alpha over k. Actually, how do we write it? Maybe in more abstract sense, we say that you take all its conjugates. You take all its Galois conjugate. Actually, these are what we call as Galois conjugates. We know that one is there, alpha will be always be there because one of the automorphism will be identity automorphism. So rest of them we call as sigma alpha, sigma 2 alpha, sigma. We call it as Galois conjugates of alpha. So you take all distinct Galois conjugates and you can use them as a root to find the polynomial. This is roughly we use the language more standard. Right. So thus it's very easy to write a irreducible polynomial provided your extension is a finite Galois extension. Right. Now we know a recipe how to write. Suppose knowing this, let's do this example. And my alpha is this once, and for other case, my alpha is this. Can we write irreducible polynomial for alpha 2 power 1 by 3 without knowing? Let's say we don't know. We know. Suppose we don't know, we want to use the recipe. Can we use the recipe?
Alpha power?
Yeah, so for me, alpha is 2 power 1 by 3. My extension is this. We know that this is Galois. I pick up this element inside my field and I want to know what is the irreducible polynomial of alpha over q. Suppose we don't know it. I know that we all of you know about this polynomial. We don't know. Let's assume that and use the recipe. Recipe says you take out all Galois extension, right?
So first we will have to list out all possible uh, here, Q automorphisms.
Exactly. So let me just quickly write them. So sigma 1 is, we will only do for alpha only. So q 2 power 1 by 3 omega 2. So where will 2 power 1 by 3 go and where will omega go? That will define all automorphisms. So one is this identity. Other is, maybe you can tell where 2 power 1 by 3 can go.
2 power 1 by 3 omega.
Yeah. And
where
do you want to send omega?
Omega squared.
Let's keep first omega fixed,
Okay.
right? Then we, yeah.
The last one.
Hmm.
So totally we'll get 6.
Right, exactly right. So I will just permute them by taking now omega square. First I fixed omega and I changed 2 power 1 by 3. Then I change both. Right, so all right, these are all 6, right? Sigma 1, sigma 2. Oh, they are not all. I think something is left. What is that? 2 power 1 by 3 going to 2 power 1 by 3 omega 1 to omega square. Yeah, this is sigma 6, let's say. So, okay, where does 2 power 1 by 3 goes under all automorphism? I have to check what are the distinct possibilities, right? So this automorphism, I'll just highlight. This will fix 2 power 1 by 3. This will fix 2 power 1 by 3. So sigma 1 alpha is 2 power 1 by 3. I will write first this set. This goes to 2 power 1 by 3, right? This also go to 2 power 1 by 3. So I will just write once. This set I have to take once, okay? This and this, they both goes to 2 power 1 by 3 omega. I will take again one possibility. They both will give 2 power 1 by 3 omega squared. Again, I will write this. What does recipe says how to write the irreducible polynomial? x minus
x
sigma.
minus 2 power 1 by 3.
Hmm.
X minus 2 power 1 by 3 omega.
Right.
X minus 2 power 1 by 3 omega squared.
Yeah, so from here, can we say it is same as this? Well, it will be. We will use this
Okay.
fact, I think.
1 plus omega squared is 0.
Exactly. So we will use this fact to say that this
Yes.
is equal.
Omega cube equal to 1.
Yes, omega cube equal. And we will use the powers also. Omega power 4 is omega, like that. If somewhere comes, I don't think that will come, by the way. It will not come. Right. So I think this will give me all, provided I don't know. In this case, I know it. Okay, now let's go to one. I think this is one question that I have taken from the lectures. I want to repeat if you want, otherwise, I will not repeat it. It says that if my extension is CT means it's a polynomial, rational polynomials, where f and g are from CT. That means coefficients can be complex, like this a naught plus I times a1 plus t times a prime plus ib prime plus t square. Coefficients are from C, and polynomial is in one variable t. Right, so this is my field, and if I take sigma 1 automorphism, which send t to it, and sigma 2 which maps t to 1 by t, let's say, which I'm calling t inverse, then k over kg is a Galois extension. This is anyway we know this is equal to order j. That is a Galois extension. Kg is mod g. This we know. What is the irreducible polynomial of this t over kg? For that, one has to first know what is kg. Then only one can talk about irreducible polynomial. So I think I'm just repeating few things which I found interesting in the lectures. So do you want me to repeat or you can read yourself?
Because he has already proved that t power 4 plus t power minus 4, that element, t of that.
Yeah. Yeah, so I think he has proved that kg is same as p t power 4 plus t minus power. This is what he got the field, I guess.
Yes.
And
Yes.
then he want to know c t over c t4 plus t minus 4 over c. He wants to know what is the irreducible polynomial of t over ct4 plus t minus 4. That means coefficients are like this. Let me write again what is the meaning here. Meaning is your functions ft by gt, where ft looks like a naught plus I time a1 times t4 plus t minus 4 plus a naught prime plus I times a1 prime, then t power 4 plus t power minus 4 whole square, and so on. This should be treated as one variable z, just like z square, z cube. I think this is clear, right? I mean, not t, maybe z. All right, so we want to know, can we do this? Can we find a irreducible polynomial? For that, one has to see that this is my k, this is my kg, and therefore g, we have fixed two automorphisms, sigma 1, sigma 2. Well, he has fixed many, sigma 1, sigma 2, sigma 3, sigma 4, and sigma 5. It's a group generated by sigma 1, sigma 2, right? I think. Um,
Group generated.
yeah, so then you have several t going to it. So this is one. If you power, take its power, that will be minus t. Mm, that means it's a sigma 1 composing sigma 1 t. It, and then going again it to be I square t, which is minus t, right? Sigma 1 cube will be minus it, and then sigma 1 4 will be t. So there are many, like t going to it, T going to minus T, T going to minus IT, and T going to T is anyway fixed. And then T going to T inverse. There are several many, and then one has to take all possible images of T and then their product. Um, so you have to also take sigma, it's a group generated by that. So elements are like sigma 1 square, sigma 2 square, sigma 3 square, sigma 2, sigma 1, sigma 2, sigma 1 square, sigma 2, sigma 2. I'm sorry, so sigma 1 cube, sigma 1 4 is identity. Sigma 1, sigma 2, sigma 1 square, sigma 2, sigma 1 cube, sigma 2, and these are all 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is the all possible elements of the group. You have to take all images of T under all these automorphisms, and then you will get 8 many, and all will be distinct. This is how this has been done in the class, I think. And all roots you take and then find a polynomial with that 8 roots. You will get a 8-degree polynomial over this. Right? This is okay, right?
Yes.
Yeah, I just want to say that this is group generated, not just 2 elements. Therefore, one has to take all 8 automorphisms. Yeah. All right. So I think with this question is done. We'll go to question number 7, where I want to know what are all equivalent statement to say that a finite extension is Galois, because now we know there are several ways to check whether a finite extension is Galois or not. I just want to write it once so that you can also recall all the time. So do you remember? You can also shuffle your notes if you want.
Fixed field of this
Okay.
GKF equal to F itself.
Yeah, so F is the fixed field of K under G, where
Yes.
G is the set of all F automorphisms of K. So in fact, group. Yeah. Right. So if that is there, then we say that this if and only if G over F, sorry, K over F is Galois. Any other? What about index? In terms of index, can you say?
K over KF
Yeah, K over F.
equal to order of G.
Exactly. This is same as if and only if K over F is Galois. Right. Anything else?
So K is the splitting field of a separable polynomial.
Very nice. This is the split. Yeah, this is we did today only. Splitting field of a separable polynomial over F. Right. This is also if and only if Q over F is Galois. Anything else? I think this is also true. This is normal and separable extension. Then also K over F is if and only if K over F is Galois. This is also true, I guess. Right. So roughly these are all. Roughly this is all. So I guess we know now several ways to check, and mostly this is the most useful we find, or equivalently this. They are anyways almost same thing that we want to say. These are most useful. Right. So okay, now another question is we want to list all intermediate fields between Q and Q zeta 8, where zeta 8 is the root of unity of order 8. This is important. There are several roots which do not have root 8, but they are roots of 8th roots of unity. All right, so let me write what we want. We want Q z, zeta 8 over Q, where zeta 8 is the root of 8th root of unity with order 8. So what, how do you write all possible, let's say 8th roots of unity? There should be some way root to write, right? All roots.
Roots of unity.
Yeah, so
Cos 2 pi I by 8 plus I sin 2 pi by 8. 2k pi by 8.
right. So among this, which one do you say this has always rule? I mean order 8.
Order 8 when
Yeah, among them, let's say this is all or t2 pi I k by 8. This is same thing.
for
So if you look at t2 pi I k by 8, you have to raise its power such that it becomes 1. And you want that, you want to raise its 8th power, then only it should be 1. Which k you should choose?
those cases which are co-prime with 8.
Yeah, so as simple, exactly right. So what will I choose? Is it enough to choose k equal to 1? Is 1 co-prime to 8?
Yes.
You can choose 3, you can choose
Yes.
5, you can 7, everything. Right, so I choose, let's say I choose k equal to 1. That's that simple. So 2 pi I by 8, this is a root zeta 8 that we want, let's say. Suppose this I'm choosing. We want to know the all possible subfields between them. So from here, it's not that difficult to know what is this root. Can you see more? How, what kind of root is it? This is not difficult, right? It's I pi I by 4. Do you know this? Cos pi by 4. Okay, so let me recall. This is 1 by root 2. Both are 1 by root 2. This is okay, right? I'm just taking simplicity because here we can describe the structure about this root. Can you see it? Like, is this okay?
Yes.
Okay. So I will rewrite my extension like q 1 by root 2 plus I by root 2 over q. Can I rewrite this extension?
Root 2 comma I. Q of root 2 comma I.
Exactly, exactly. So q root 2 comma I is same as q 1 by root 2 plus I by root 2. This is a simple check, so I will leave. You can see that this is always contained here. Sorry, this is contained here. This is simple, right?
Yes.
However, you have to check the other way also. That is a simple exercise that you can check. All right, so these are two same extension that needs a proof. All right, so suppose that these two extensions are same. Then now, what can we say about the intermediate fields between this and this? Yeah. So we have, let me rewrite. Our finally extension has been reduced to this form. Can we say what are the subfields directly? If not, then we will go to fundamental theorem of Galois theory. First of all, is it Galois? Can you write this extension as a splitting field of a separable polynomial over Q? Yeah.
Yes.
And what is that polynomial?
X squared minus 2 into x squared plus 1.
Exactly. This is a separable polynomial over Q, and Q root 2i is splitting field of F over Q. Right. So it's Galois. Therefore, or I'll write Q zeta 8. They both are same, and this is Galois extension. All right. So this is Galois, and what is the degree? That is also pretty clear, right? You can use tower of fields if you need. This is degree 2, this is degree 2. All right, so this is a Galois extension of degree 4, and can we see Galois group for this? Galois group of Q root 2 comma I over Q. We have to write all sigma i's which maps root 2 and I to somewhere. Can you write all automorphisms which send root 2 and I to somewhere?
Root 2 to root 2, I to I.
Okay, this is one. Other?
Root 2 to root 2, I to minus I.
Okay, other?
Root 2 to minus root 2, I to
I to I and
I to minus I.
right. So we have 4 automorphisms, and you can see the order of each automorphism is 2. Therefore, this group we already seen it is Z2 plus Z2, not Z4. All right. So what are the subgroups now? Suppose we want to know all possible subfields. So we saw from tower that root 2 is there. Can you tell me one more extension which is contained inside this and containing Q? We want to know these. So can you think right now at any field in between other than Q root 2?
Q of root 2 plus I.
Okay, Q of root 2 plus I. But what if I say that this is same as Q root 2 comma I? This is my claim. This is my claim. You can check. One containment is there, right?
Yes.
Root 2 plus I is contained there, but you can check that this element is actually the element which will generate this. So this is what we call as primitive. Maybe we will come back. So I will give a proof saying this. Maybe I will give a proof. But for time being, you don't take this. Any other field? Simple. Go simple. I think you'll get it. Just like Q root 2. You can write one more.
Q of I.
Exactly, Q of I. But I say that there is one more. Maybe you cannot see right now. Let's see. So Z2 cross Z2. What are the possible subgroups of this group? What is cardinality, first of all?
4.
4.
Four.
So you know that by Lagrange theorem, any subgroup should divide 4, right?
Yes.
So possibly what are the numbers that can divide 4?
So 1, 2, 4.
Any subgroup if you have that should have this order. This you know by Lagrange theorem.
Yes.
Now, this is one subgroup that you know. Can you give me other subgroup which has order 2? Or it does not have? This is order 1, 4. Yeah. Suppose you have H cross K. This is a group. How can you write the subgroups of this group in general?
Taking subgroups of H and subgroups of K.
All right. Since you know this, can you tell me here subgroups
So
of H,
here we
subgroup
have
of
only singleton 0 and then Z2. They are the
yeah, yeah. So subgroups of Z2 are this or this. Now can you tell me order 2 subgroup?
E and
Simple. You are there.
we have 4,
Sorry.
4 subgroups.
Okay, we have how many? 4 subgroups. What are these?
That E comma E 0 comma 0.
0, comma 0. Okay, that means just identity. Okay.
0 comma Z2.
0, comma Z2. It means like this, I guess. So
Yes.
this is what we mean by this cross Z2. Yes.
And reverse it.
Exactly, reverse it. That means this and Z2 cross Z2, right? These are isomorphic, right? Why they are isomorphic? You can find an isomorphism, right? By writing a map E comma A, you map it to A comma E. This is an isomorphism, right? So up to isomorphism, we have 3 groups here, subgroups. You can write either of them. These are all possible subgroups. You agree, right?
Yes. So
All
3.
right.
Yes.
So, yeah, we have 3 subgroups of Z2 cross Z2, which are trivial, non-trivial, everything. Like we have this up to isomorphism, I'm saying, because we have other also by changing, interchanging, but up to isomorphism, we have this. Right. Now, let me write a tower now. We have Q root 2 comma I and Q. And between, we don't know. And here, the group has to be written in the base. Okay. Now, if I take the trivial group, what is if I take the trivial group, then you know that it's taking this as a group, let's say H. Then corresponding, it's a field which you get here will be fixed field of this, right? Where this is K, this is F. This is how we define, right? The isomorphism between the groups and the fields. If you have group, you take the fixed field of that group. And if you have field, you take the Galois of that K over L. You agree, right? Maybe I will go back. Fundamental theorem. Yeah. If you have group, subgroup H, you have to go to field. You take the K is the extension that you have, K over F. You take the fixed field under H. And if you have a field, then from there you take the Galois group of K over the field itself, L. This is okay, right?
Yes. So
Okay,
now we are
now
coming from subgroups to fields.
exactly. So we are understanding the concept of fields through groups by knowing the concepts at group level. Since we have only one subgroup, so this subgroup, can you find, I mean, of course, up to isomorphism we have one, but if we take the other one, let's say Z2 cross this, then what is the thing that we can say? These are up to isomorphism.
So you were asking what is the intermediate field corresponding to the subgroup E.
I think I did not spend some time here on the group, maybe. So also we have group, but no, that okay. I'll just okay. So group is Z2 cross Z2, but let's write that explicitly. We have E, we have sigma 1. E means identity. Sigma, let's say sigma 1, I will write sigma 1, sigma 2, sigma 3. These are all. This is mapping root 2 to minus root 2 I to I. This is root 2 to root 2 I to minus I. And this is both minus to minus. From here, let's say don't go to the group structure itself. You can find several subgroups from this, the structure of the group itself. Can you find that subgroups? I know that up to isomorphism they are there, but you have to write all the subgroups possibly. But number of elements will be same, but as you say, 1 comma sigma 1, 1 comma sigma 2, 1 comma sigma 3, up to isomorphism, they all are C2. The groups are isomorphic to C2 only. But the structures are different. Structures are different. So here we want to know what are the fixed field of these subgroups. Let's say this is H1, this is H2, this is H3. And we saw bijection is, maybe I'll write in this way now. H1, H2, H3. Yeah, so I will say with respect to H2, with respect to H1, there are fixed fields. We call them as KH, KH2, and KH3. This is okay. This is by the definition of, by the theorem itself. We are not introducing anything new. Now, what are KH1? All those alpha in K. How to write an element of K? K is Q root 2 comma I. Right? You have to write an element like A0 plus A1 root 2 plus A2 I plus A3 root 2 times I. This is okay, right? Basis is 1 root 2 I root 2 I. Now, if you see under sigma 1 root 2 going to minus root 2, they will change. And if you want to keep fixed, what will be kept fixed? Qi, right? I will be fixed. Root 2 will change. You see for this sigma 2, I will change. Q root 2 will be fixed. And for the last one, you will not have anything other than product. The last product element, because both their sign will be negative, but product will be again positive, and this will be fixed. This will be fixed. So correspondingly, what are the fields that we got? This, this, this. And since number of subgroups are these many only, you have these many only possibility as a subgroup. Therefore, because you know that it's order 4, order 2 are the only possibility subgroups. And these are all 3 order 2 subgroups. As groups, you can say there are isomorphism. You can give an isomorphism, but you have to write different subgroups. And therefore, you will see that each subgroup will give me each fixed field. And now if I write a tower, the tower will be like this. Q root 2, comma I. One is Q root 2, if you have seen. One Q root Qi, you gave it to me. I think you remember this. You told me. The other third one which I gave now is this one. Now why it is distinct? Can you see that this is not equal to q root 2? It's not equal to qi. None of them are equal. Can you see that?
Yes.
Yeah, so none of them. So we have how many total fields, total intermediate fields between Q? Three, right?
3, or can we say 5?
Okay. Maybe. I wanted to know between this and this how many. My question is between this, not like total. Okay, but we can write, of course. Total fields, we can write, let's say 5. All right. So I think this is what I wanted to say about this question. And now let's do some more thing. We have some more time. Let's do Q and Q 2 per 1 by 4. I think this is little more involved. I will do this Q 2 per 1 by 4. Q 2 per 1 by 4 over Q. Notice that how to find all. Let me repeat the whole idea. Idea is to check whether it is Galois first of all. It is Galois, that one. Is it Galois or not? That one can check. If not, then one has to look at the Galois group first of all, because the groups are which are going to be the intermediate fields. So if you write the Galois group here, it is, what is that, by the way? It's just trivial, right? So I think mm, it confused. Yeah, we have to list all the intermediate fields between Q and Q2 per 1 by 4. That's correct. Yeah, and then we went to the possible groups that we have. Right, so in this case, we have x power 4 minus 2 is the polynomial which has root in Q2 per 1 by 4. However, this is not Galois, right? This we know. But still, it can have subfields, right? Who says that we cannot find the subfields? We still can find the subfields. So what is your thought about this? How do we proceed, first of all, knowing that this is not Galois?
So we cannot apply that fundamental theorem.
Yeah, we cannot apply fundamental theorem, but we can apply provided we can further find a normal and separable extension, and there we can find the subfields. Is that okay?
Okay.
Yeah, so what we do, we can simply find the extension which is Galois. And for that extension over this, we find all subfields. Now, all fields lying between this and this, can we among them, can we find that which are those which contain inside Q2 per 1 by 4? That one can do, right? At least what I'm trying to say, is that clear? So, okay, maybe I'll repeat. So, for this as an extension over Q, here we can apply fundamental theorem to find all intermediate fields. And among them, check which are subfields of Q2 per 1 by 4. Is that okay?
Yes.
So this will answer the question, and I think I will write answer. I cannot, I think, if you want, I can discuss this whole thing. So 2 power 1 by 4 comma I to Q. What is the degree?
So degree
What is the
is
degree?
8.
Degree is 8. How? What is the separable polynomial for this?
Separable polynomial is x power 4 minus 2 into x squared plus 1.
Exactly right. This is the separable polynomial. And Q 2 power 1 by 4 comma I is splitting field of this separable polynomial f over Q. Therefore, this is Galois. Right. And this extension is in fact degree 8 extension. So correspondingly, we will have a group also. So if you look at once again, so I think if you recall, sigma I is like Galois group, let's say Galois group of Q 2 power 1 by 4 comma I Q, let's say over Q. This is all automorphisms. So we will just need to know where this and where this can go. Knowing the roots, now you remember all the roots that will help you to map where does I go, where does 2 power 1 by 4 goes. Can you recall all that? I try to be quick because there are several other questions. One is identity, right? Other is all roots are 2 power 1 by 4 minus 2 power 1 by 4, 2 power 1 by 4 I, 2 power minus 2 power 1 by 4 I. So I will keep first, I will keep changing roots. I will fix I. Where can I can go, by the way? What is the possibility of I?
I and minus I.
Exactly, I and minus I. So I will just repeat all the things that we did. Now I will change I to minus I and I will change 2 power 1 by 4 to all its possibilities. Yeah. So these are all A 1, 2, 3, 4, 5, 6, 7, 8. All 8 automorphisms. Is this okay? Now, let's look at possibly subgroups. So our group is, what is the order of our group? 8, right? Now, by Lagrange theorem, any subgroup should have order. What is that?
1, 2, 4, 8.
Yeah, so this can possibly be. Can you find among them? I mean, I'm asking you a question that maybe like at this moment you need to solve do some computation, then only you can tell. But I want to ask still, what is the one group, subgroup?
Identity.
Identity. What is order two subgroup? Among them,
Order
can you
2.
find any sigma 1, sigma 2, 3, sigma 4, sigma 5, sigma 6, sigma 7, sigma 8? Whose power if I compose with again, I will get that trivial map.
Composition. So that
Yeah, compose. Yes.
that I to I and I to minus I will become identity.
Exactly. There are no other, right? There are no other. Order two.
Order.
Or you can find them. Is this? Can you say something? So sigma 2 compose sigma 2 of 2 power 1 by 4. Sigma 2 compose sigma 2 of I. It is I, right? It fixes I. What about 2 power 1 by 4? It's sigma 2 minus 2 power 1 by 4. What about again? It is this. Is this okay?
Yes.
So this has also order 2. This is 1, this is 1, this is... Any other? This is also right. You change I to minus I once. Again you will change, you will get I, right?
Yes.
Same thing this. It's negative sign. You came again, once you apply, you will get back 2 power 1 by 4. Right. So I will write 1 comma sigma 2, 1 comma sigma 5, 1 comma sigma 6. All these are all possible degree 2. Sorry, what do I say? Order 2 subgroup. Any other? Any other will not have order 2 that you can see, because if you map I, if you, let's say you will see 2 power 1 by 4 going to 2 power 1 by 4 I. Let's say you want to see this. With I, there is a issue, because if you apply once again to 2 power 1 by 4, it will be sigma 2 power 1 by 4 I. Map changes 2 by 4, 1 by 4 to I. So 2 power 1 by 4 I square, it will be minus of 2 power 1 by 4. This is sigma square. If you apply sigma q, then sigma of minus 2 power 1 by 4 is minus 2 power 1 by 4 I. If you apply sigma 4, then sigma 2 to minus 2 power 1 by 4 I. This will be 2 power 1 by 4. Is this okay? Sorry, 2 power 1 by 4. So 4 power gives me identity map, sigma power 4. Wherever there is I, wherever there is I. So this is I, this is I, this is I, this is with I. So I will just say now, simply, those all are order 4. And you know their order 4 should have 4 elements. So other group is 1, sigma 3, sigma 4, sigma 7, sigma. Did I do? I repeated something or no? 1, sigma 3, sigma 4, sigma 7. One of them should be in the other. Can we write the, which one can we find it through the other one? Sigma 3. Okay, I have to check. I am not sure which one can determine the other, but as you said, as you see, there is no order 4, order 2 among the remaining. Sigma 3, 4, 7, 8, none of them has order 2 that you can see, right? All right, so maybe we can say this and see sometime later. So we have order 1, we have order 2, we will have some order 4 also, and order 8 is anyway our whole group. So let me write the idea, what exactly the idea I want to convey. Q 2 power 1 by 8 comma I, or it's 2 power 1 by 4, I guess. Over Q, the group here is, so I'll say that this is a dihedral group of D4. The group is D4. Because it has two generators, one is the order 4 automorphism, let's say sigma 4, and other automorphism is sigma 2. One order 2 and one order 4 will generate. This is my claim. Maybe next time if I have time, I will prove this. So for this group, the group is D4 because it has two generators. One is order 4, one is order 2. And if I take product of their powers, I will get all the elements of this group, Galois group. All right, so here the group is D8. And it has subgroup that we saw. It has order 8 subgroup also. It has order 8 subgroup. I will write P. Order 4 subgroup will be actually cyclic group. It has order 2 subgroup, that is C2. I think this you can say, right? So this is order, index will be 2, index will be 4, index order is 2, order is 4. So here we will have fields. With this P4, we will have certain field. Of course, I cannot write, but I will write the answer. Maybe we will discuss sometime, some more time. 2 power 1 by 4. There is one which you can see, I guess, QI. There is one more which, I think, where do I write? So we will have one more that we have, that is q root 2. We have, I guess, one more qi, then we have this also, we have this also. Yeah, I think we are done because this has, okay, I'll write this one more thing. This has C2 group and that is sitting inside this 2 and 4. So this is like degree is 2, here degree is more, this is 4, this is 2, this is 2, this is 4, sorry, this is 2. And what can you say about this? I guess this is actually containing q2 power 1 by 4 and further this. Actually, this has degree 2 and this has degree 2. This is how it has been splitted. So maybe what the question initially was to know about this. And between q2 power 1 by 4 and q. And the only which will be coming is this only. So that you can see. So q2 is, this is only which is contained inside q2 power 1 among all the list. And there is one more q2 per 1 by 4 times I. That also, that has again degree as, I guess, 4, because you can see like this contained in q2 per 1 by 4 I, further this. I guess this looks okay. This one. I think I confused you and myself. I'll be later, maybe I'll be more clear with this example. This example like needs some time. So I hope roughly what I want to say is clear. Maybe we will go in details again. We will do this again. Hello?
Yes, I'm following.
Yeah, okay. Then so I think we will do this question. This will take some more time. I'll just quickly do this one more question, which is which I feel it's good. So suppose we have a finite extension of odd degree over R, then that extension has to be actually equal to R. First of all, is the statement fine?
Finite extension of
Oh, sorry. I think screen has gone right. Now it should be visible. So any odd degree extension over real is none other than real itself. Nothing can be more than R if you have odd degree extension. So I think this has also come in the lecture class, but I felt like it is important to discuss. You remember this statement?
not it. Maybe
Okay.
last section.
Okay, so I will just roughly give solution. So if we have a odd degree extension, then there will be an element which is outside R such that irreducible polynomial will be having degree odd. This is okay, right? The irreducible polynomial of alpha, which is outside real and lying in L, should have odd degree, right? So suppose that polynomial is odd, then if I try to take its limit going to x tends to infinity, let's say my polynomial is this. If you look at it, if I take x tends to minus infinity, then where does it go? Like if I take x to be minus 100, then the first value will be minus 10 power 6, right? Plus 100 plus 1. This is extremely like big number and negative big number, right? Can you see that? This is very big and smaller than zero, very small than zero. When going towards infinity, do you see this? Hello?
So we substitute only in the higher power.
Yeah, I'm just giving that if x goes to extremely to negative, means my taking limit to be minus infinity, towards minus infinity, then it's like very like too much negative, too much. Suppose if I take x to be positive, a big number of positive, what do you say about that? Where does fx goes? A very big number. Let's say 10 power 10. It will go very far, right? Very far to zero, right? But it will be positive. But it will be positive. So important is this fact that this function can be made as negative and positive based on choosing certain points of x. Do you agree that I can make this function negative as well as positive by choosing certain x? Do you agree?
Yes.
Then I want to say it will cut. So if this function, okay, this function has negative values. So fx I'm plotting here, y equal to fx, and x I'm plotting at this point. I want to say you can find certain negative x for which the function values will be very much negative. Very much negative means it will go somewhere here, somewhere here, negative. Positive means I have this. I want to say x positive will give me positive values. That means the function is going positive for this, negative for this. That means it will cut x-axis at certain point. It will certainly cut x-axis at certain point. That means f has one real root, at least. Is this
So
okay?
okay, the coefficients are all real.
Yeah, coefficients are all real. Yes,
So imaginary roots occur in conjugate pairs. So
that's
odd
true.
degree means there must be at least one real root.
Exactly right. Exactly. I mean, the idea is this. Proof is this, and what you said, the statement is correctly. It's completely correct. So therefore, whatever polynomial you have, that will no longer remain irreducible, right? That will no longer remain irreducible, and therefore your extension cannot be a proper extension. That has to be actually odd. If it is odd, if it is even, then we know C is an extension over R, right? For odd, there is no possibilities. The choice that you made is wrong, which is this. If you take any element which is outside real, then it has a irreducible polynomial of odd degree, which is not possible. That means your element outside L is not possible. That means every element actually lies in R, and therefore there is no element. And therefore extensions are same. Is this okay?
Yes.
All right. So therefore, this is more or less done. All right. There is one more proof you can read also. I have written one more proof. This is in terms of intermediate value theorem. This is using that. Now, we don't have much time left. So I want to actually discuss Thilo theorems. Shall we leave this part for next session, or do you want to discuss now?
So all the Sylow's theorems are included in this Sylow's theory, or
Well, some result you may use somewhere. So I just want to recall, and I want to use some. I want to give some basic exercise based on Taylor theorem. So maybe if you want, you can read it somewhere, or we can discuss.
maybe we can discuss in the next class.
Sure. All right, then I will stop here. I will stop the recording, and then this recording will be available to you.
Okay,
Thanks
thank
for
you.
reminding. Yeah. Okay. Thank you.